Unseen roads stretch across the cosmos, guiding particles on near-light-speed journeys. These are the invisible highways, a secret network governing the flow of energy and matter throughout the universe. By the end of this, you will see the cosmos not as a collection of isolated objects, but as a single, interconnected system. We will trace how a single particle born in a dying star can influence the formation of a galaxy billions of years later. What hidden force directs this cosmic traffic, and how does it touch our own existence? The answers redefine our place in the universe. What does it mean to live in a world built by particles we cannot see? This cosmic web is the fundamental architecture of everything we see. Think of it as the universe's skeleton, an immense framework of dark matter and hot gas tracing out filaments that stretch for unimaginable distances. Between these threads lie the great cosmic voids, vast empty regions of near-nothingness. This is not a random scattering of stars and galaxies. It is a highly organized structure, a network of roads and intersections on the grandest possible scale. Galaxies themselves are not sprinkled randomly through the darkness. They form along these dense filaments, and they cluster powerfully at the nodes where these pathways cross. It is at these bustling cosmic intersections that the largest galaxies in the universe are born and grow. How do we even begin to map something so vast and invisible? Scientists use the light from millions of galaxies as tracers. Projects like the Sloan Digital Sky Survey have painstakingly charted the positions of countless galaxies, and the pattern that emerges is unmistakable, a web of structure woven across the cosmos. This map reveals that the empty space of the universe is anything but empty. It is filled with this hidden architecture, a scaffold that has guided the growth of all cosmic structure since the beginning of time. The very existence of this web dictates the fate of matter, funneling it along specific routes for billions of years. So, who are the travelers on these ancient roads? Our traveler is a single high-energy proton, born in the chaotic aftermath of a star's violent death. It surges outward from a supernova remnant, a cosmic accelerator of unimaginable power. Shock waves from that ancient explosion have hurled it into the void, granting it nearly the speed of light. This proton is a cosmic ray, one of countless charged particles that endlessly crisscross the galaxy. But it does not travel in a straight line. It rides the curves and spirals of the galaxy's own magnetic field, tracing an invisible highway that guides its path. These magnetic field lines are the rails upon which our proton surfs, a twisting, turning journey that can last for millions of years. The discovery that these rays came from beyond our world was a revelation. A physicist named Victor Hess took instruments high into the atmosphere in a balloon and found that radiation increased with altitude, proving its source was not the Earth, but the cosmos itself. These particles carry the fingerprints of the most violent events in the universe. When they finally reach our world, they do not strike the ground directly. Instead, they collide with the upper atmosphere, shattering into a shower of secondary particles, a faint, detectable echo of their epic journey. By studying this cosmic rain, we can work backwards. We can begin to understand the powerful engines that launched them, the shock waves that gave them such incredible energy. What secrets about stellar explosions and galactic magnetic fields are encoded in their relentless, invisible flow? These travelers are just the beginning, setting the stage for particles with journeys even more strange and profound. While our proton surfer navigates the galaxy's magnetic curves, another traveler moves with ghostly indifference. It is a neutrino, born in the heart of the sun's nuclear furnace. This particle is so ethereal it can pass through a light year of solid lead without a single interaction. It feels no magnetic pull, it bends for no obstacle. Its pathway is a perfectly straight line, a cosmic freeway cutting directly through the universe's tangled web. This is what makes neutrinos such perfect messengers. They carry information in a pure, unaltered state, flying directly from the most violent events in the cosmos to our detectors. When a star explodes as a supernova, the vast majority of its energy is actually released in a sudden burst of these ghostly particles. They escape the cataclysm long before the light does, bringing us the first news of a stellar death. Yet catching this news is one of the greatest challenges in modern science. To even have a chance of detecting a handful of these phantoms, we must build massive traps. Imagine the ice cube Neutrino Observatory, a cubic kilometer of pristine Antarctic ice embedded with thousands of sensitive light detectors. It uses the entire planet as a shield, waiting for that 1 in a billion chance that a neutrino will interact with an atom in the ice and create a faint flash of blue light. This monumental effort paid off, allowing scientists to trace a single high-energy neutrino back to a blazar, a supermassive black hole at the heart of a distant galaxy, violently spewing jets of radiation. That single particle, after traveling for billions of years in a perfect straight line, pointed directly back to its monstrous source. How do neutrinos provide a clear view of cosmic cataclysms that other particles obscure? They are the universe's most reliable couriers, delivering a pristine letter sealed at the moment of creation, its contents untouched by the long journey. Yet even these perfect freeways hint at a deeper complexity, inviting us to consider particles that are not free at all, but are guided by forces far more subtle and strange. Light itself rides the ultimate cosmic freeway, a photon racing from a brilliant quasar when the universe was young. This particle of pure energy travels a path dictated by the shape of space itself, a route bent and warped by every galaxy and dark matter halo it passes. Its journey is a direct testament to Einstein's vision of gravity, not as a force, but as the curvature of spacetime. We see the evidence in gravitational lensing, where the light from a distant galaxy is warped into a perfect ring or a stretched arc by an invisible mass in the foreground. This is the electromagnetic expressway in action, a highway system built from the fabric of reality. Astronomer Edwin Hubble's observations of this light revealed a universe in motion, with galaxies rushing away from us, their light stretched into longer, redder wavelengths. This cosmic redshift is the Doppler effect on a universal scale, and it tells us the universe is not static, but dynamically expanding. Every photon that reaches our eyes carries a story. Some have traveled for billions of years, their color subtly shifted by the expansion of space, their paths gently curved by unseen matter. They form the backbone of all observational astronomy, allowing us to see the first stars, map distant galaxies, and even detect the faint afterglow of the Big Bang itself, the cosmic microwave background radiation. Yet their journeys are not always straightforward. Interstellar dust can dim and redden them, while magnetic fields can subtly twist the direction of their oscillation, a property we call polarization. What stories do these ancient messengers carry? They tell us of the universe's violent youth, its gradual evolution, and its eventual fate. They show us how the visible highways of light are deeply intertwined with the invisible scaffolds of dark matter and gravity. This intricate network of particle pathways, from magnetic surfers to ghostly neutrinos and these messengers of light, points toward an even more fundamental question. What is the nature of the roads themselves, and the unseen material that builds the cosmic map? The sun itself is a source of a constant, invisible river. This is the solar wind, a supersonic stream of charged particles flowing outward in all directions, defining the very boundaries of our solar system. It carves out a vast protective bubble in the interstellar medium known as the Heliosphere. Guiding this relentless flow is a colossal, undulating structure called the heliospheric current sheet. Think of it as a giant, wavy skirt around the sun's equator. a fundamental highway where the sun's magnetic field flips its direction. Charged particles from the solar wind ride this immense, rippling wave as it spirals outward, shaping their journey through the void. Our first direct encounters with this river came from pioneers like NASA Voyager probes, which sailed through this stream for decades, tasting its composition and measuring its changing speed. These spacecraft revealed the solar wind is not a steady breeze. It gusts and calms with the sun's own stormy activity, from the relatively slow wind of its equatorial regions to the fast, intense streams that burst from coronal holes. When this river of particles encounters a planet like Earth, it does not simply wash over us. It crashes into our planet's magnetic shield, the magnetosphere, compressing it on the day side and stretching it into a long tail on the night side. Some particles are funneled down toward the poles, where they collide with our atmosphere and ignite the breathtaking dance of the auroras. But this beautiful interaction has a powerful, disruptive side. Intense bursts from the sun, like coronal mass ejections, can send shockwaves through this particle highway, triggering violent space weather. These solar storms can induce powerful electrical currents in the ground, threatening power grids and bathe our satellites in radiation, disrupting the global communications we rely on. By studying the solar wind's composition and speed, we are essentially taking a remote sample of the sun's incredibly hot outer atmosphere, the corona. It is here that mysterious processes heat the gas to millions of degrees and accelerate particles to escape velocity, allowing them to break free from the sun's immense gravity and begin their journey toward us. This dynamic particle pathway is our most immediate and tangible connection to a star's influence. It demonstrates how a continuous stream of invisible particles shapes the entire environment of our planetary neighborhood, a constant reminder that we live within the extended atmosphere of our sun. This local current of particles is just one small part of a much grander circulation, prompting us to look beyond our solar bubble to the galactic winds that flow between the stars themselves. These magnetic rails are not passive guides. They are dynamic forces, actively shaping the paths of nearly every charged particle in the galaxy. Generated by the churning motion of conductive plasma within stars and across vast galactic scales, these fields act as cosmic traffic controllers. They can focus a diffuse cloud of particles into a narrow, powerful beam, or accelerate them to staggering energies. Research from institutions like the Max Planck Institute reveals how these invisible structures sculpt the very substance between the stars, the interstellar medium, creating a complex web of channels and barriers that dictate how cosmic rays move. A particle can become trapped, bouncing back and forth between magnetic mirrors in a configuration known as a magnetic bottle, held captive for eons. Or it can be directed with precision, forced to spiral tightly along a field line. This spiraling motion is not silent. Electrons whipping through these curves emit a unique form of light called synchrotron radiation, a brilliant beacon that allows us to see the outline of the magnetic field itself in spectacular nebulae and jets from black holes. This steering effect is fundamental to the most violent events in the cosmos. In a solar flare, magnetic fields reconfigure in a cataclysmic snap, releasing immense energy and hurling particles across the solar system. Around a rapidly spinning pulsar, the magnetic field acts like a colossal lighthouse, focusing its particle wind into two intense beams that sweep across the galaxy. Without this pervasive magnetic guidance, the universe would be a chaotic jumble of particles crashing randomly into one another. Instead, we see ordered structures, focused jets, and predictable pathways. How do we begin to trace the routes of these energetic particles guided by such invisible hands? These natural particle accelerators operate on a scale that dwarfs anything we can build on Earth. The process often begins with a simple bounce, a particle trapped between two approaching magnetic mirrors. Enrico Fermi realized that a charged particle could gain a tremendous amount of energy from this kind of repeated reflection, much like a tennis ball being volleyed back and forth between two rapidly approaching rackets. In a supernova remnant, the expanding shock wave from the exploded star creates a perfect environment for this. The shock front itself acts as a moving magnetic wall, and particles can bounce back and forth across it countless times. With each crossing, they steal a little energy from the wave's motion, accelerating to a significant fraction of the speed of light in a process we now call Fermi acceleration. This is the engine that powers the cosmic ray surfers we discussed earlier, turning the chaotic aftermath of a stellar death into a powerful natural accelerator. But supernovae are not the only cosmic power plants. Consider the environment around a supermassive black hole in an active galactic nucleus. Here, particles can be accelerated by immense gravitational and magnetic forces, funneled into jets that stretch for thousands of light years. These jets are essentially particle cannons firing into intergalactic space, and the particles within them reach energies that are almost incomprehensible. Even more extreme are gamma-ray bursts, the most luminous explosions in the universe. In a matter of seconds, they can release more energy than our Sun will emit in its entire 10 billion-year lifetime, producing a flash of the highest energy photons known to exist. These diverse mechanisms all share a common purpose. They convert the raw, chaotic energy of the cosmos into the ordered, high-speed motion of particles. They are the power stations feeding the invisible highways, ensuring a constant flow of energetic travelers. Without them, the cosmic web would be dark and silent. How do we reconcile the sheer violence of these sources with the precise, guided pathways these particles then follow? The acceleration is only the beginning of the story, setting the stage for a journey that will ultimately define how these particles shape the cosmos they travel through. That proton, accelerated to near light speed, does not travel forever in empty space. It eventually encounters the thin, scattered material that fills the galaxy, the interstellar medium. This is not a true void, but a cosmic obstacle course of gas, dust, and plasma. Imagine our high-energy proton, after its long journey along magnetic rails, slamming into the nucleus of a simple hydrogen atom drifting in a cold, dark cloud. The collision is catastrophic. The proton shatters, its immense energy transforming into a spray of new, secondary particles and a flash of high-energy gamma-ray light. This is not a rare event. The entire Milky Way glows with a faint, diffuse gamma-ray haze, a testament to countless such collisions happening every second. NASA's Fermi Gamma-Ray Space Telescope has mapped this glow, and the map is breathtaking. It reveals the silhouette of our galaxy not in starlight, but in the light of destruction, a ghostly outline traced by cosmic rays interacting with the gas between the stars. This interstellar medium is a paradoxical environment. It provides the very gas that cosmic rays interact with to produce the light we see. Yet it also acts as a barrier, slowly robbing those same particles of their energy over millions of years. A dense molecular cloud can bring a cosmic ray's journey to a grinding halt, its particles absorbed or scattered, their energy dissipated as heat or light. Yet, in a beautiful feedback loop, this very process can be a trigger for new life. When a shock wave from a supernova laden with cosmic rays plows into a cold gas cloud, the immense pressure can compress the gas, overwhelming its internal support and causing it to collapse under its own gravity. This collapse is the first step in the birth of a new star. So these particle collisions do not merely destroy, they also create. They help initiate the chain of events that leads from a diffuse cloud of hydrogen to brilliant new suns and potentially new planetary systems. The composition of the medium itself dictates the story. A region rich in heavy elements, seeded by the ashes of long-dead stars, will interact with cosmic rays differently than a pristine cloud of pure hydrogen and helium. These interactions are fundamental to the chemical evolution of the galaxy, influencing which elements are available to form rocky planets like our own. How do we begin to predict the journey of a single particle through such a complex and changing environment? The answer requires building a dynamic model of the galaxy itself, a digital twin to simulate the endless flow of traffic on these invisible roads. To understand this chaotic journey, we must turn to the power of digital creation. Supercomputers now run simulations that trace the paths of not just one, but billions of particles as they navigate a modeled galaxy. These are not simple animations, they are complex virtual universes built from the fundamental laws of physics. Within them, particles experience diffusion, bouncing off magnetic irregularities like pinballs. They are swept along by convection, carried by large-scale winds of galactic plasma. They steadily lose energy through collisions and radiation, a process that slowly dims their power over millions of years. One of the most powerful tools for this is the Galprop code, a digital engine that simulates cosmic ray propagation throughout the entire Milky Way. It ingests real observational data, from gamma-ray maps to radio surveys, and uses it to refine a dynamic model of our galaxy's invisible infrastructure. The goal is to rewind the cosmic tape, to see if the simulated journeys of these particles produce the same sky we observe from Earth. This computational work has been crucial in solving a modern cosmic mystery. Instruments like the Alpha Magnetic Spectrometer on the International Space Station detected a curious excess of positrons, the antimatter counterparts to electrons. Simple models predicted fewer of these particles, so where were they coming from? The simulations provided a compelling answer. By modeling the nearby pulsars, the spinning corpses of dead stars, researchers showed these objects could be the source, accelerating positrons that then travel to us along the local magnetic highways. The excess was not necessarily a sign of exotic dark matter annihilation, but a signature of our galactic neighborhood. These models allow scientists to run experiments that would be impossible in reality. They can turn off certain particle sources or alter the strength of the galactic magnetic field, and watch how the simulated sky changes. They can test whether a particular cloud of gas or a specific supernova remnant is responsible for the particles we detect. This is how we bridge the gap between the raw data from our telescopes and the grand story of the cosmos. The simulation becomes a laboratory for the universe, a place where we can finally watch the invisible traffic flow. But what happens when this flow is not a gentle stream, but a violent, focused beam from the most powerful engines in existence? While our simulated models trace the paths of known particles, the cosmos is filled with travelers that defy this classification altogether. These are the particles of dark matter, an invisible substance that flows through the galaxy in a vast, sprawling halo. Their presence is not revealed by light or magnetic fields, but only by the undeniable pull of their gravity. Astronomer Vera Rubin's pioneering work on galaxy rotation curves provided the crucial evidence. She found that stars at the outer edges of galaxies orbit just as fast as those near the center, a motion that defies the laws of gravity if only visible matter is present. Something unseen, a dominant but invisible component, must be holding these galaxies together. This missing mass shapes the universe on the grandest scales, its gravitational scaffold guiding the formation of the entire cosmic web. The particles themselves, if they are indeed weakly interacting massive particles, or WIMP, would be profoundly alien travelers. They would feel gravity, but they might be utterly blind to the electromagnetic force that dictates the path of every proton and photon. A WIMP could pass through our entire planet as if it were not even there. Its journey a lonely trajectory through space, dominated only by the gravitational landscape. These trajectories are not random. As dark matter flows through the cosmos, it can organize into dense streams and caustics, like traffic merging on a cosmic freeway. These are regions where the density of particles is dramatically enhanced, creating bright spots in an otherwise dark sea, and offering our best chance for a detection. Experiments deep underground, like the LUX and Xenon projects, are built as ultra-quiet listening posts. They wait in profound isolation, shielded from the cacophony of cosmic rays, hoping to record the minuscule vibration, the faint flash of light, that would signal a dark matter particle gently nudging an atomic nucleus. What clues do these elusive travelers hold? They could be the key to understanding why the universe looks the way it does, why galaxies exist at all. Their hidden pathways are the ultimate expression of the cosmic network, roads built from gravity itself. This search for the universe's missing mass naturally leads us to another profound mystery: the strange and fleeting routes traveled by its mirror image, antimatter. A positron, the mirror image of an electron, rides the same magnetic rails but carries an opposite charge. Born in the violent winds of a pulsar, this antimatter particle travels alongside its cosmic ray cousins, yet it holds a far more explosive potential. Its entire existence is a race toward a single, definitive moment: annihilation. When it finally encounters a normal electron drifting in the void, the two opposites vanish in a flash of pure energy, releasing two gamma-ray photons that streak away into the darkness. This is the signature of antimatter's journey, a reverse highway whose destination is not a place, but an event, a brilliant spark of mutual destruction. The detection of these positrons in space is a profound puzzle. The Alpha Magnetic Spectrometer, mounted on the International Space Station, has carefully counted the particles raining down on us and found a surprising overabundance of them. There are more positrons arriving than our standard models of cosmic rays can easily explain. This unexpected surplus ignited a fierce debate among scientists. Are these particles coming from relatively nearby pulsars, the spinning neutron stars that can generate intense winds of electron and positron pairs? Or could they be the long-sought signal of dark matter particles annihilating in the galactic halo? Each source paints a dramatically different picture of our universe's hidden workings. What makes these antimatter pathways so crucial is their rarity. In a cosmos dominated by ordinary matter, every positron is a fugitive, destined for a final, brilliant confrontation. This asymmetry, the fact that the universe is not made of equal parts matter and antimatter, is one of physics' greatest mysteries. By tracing the routes of these rare antimatter travelers, we are essentially investigating a crime scene on a cosmic scale, searching for clues about why anything exists at all. The annihilation signals we detect are more than just flashes of light. They are direct reports from the front lines of a fundamental conflict. These reverse highways are not just passive trails, they are active probes of the most energetic environments. When we map the gamma rays produced by positron annihilation, we are effectively creating an image of where antimatter is meeting its end. This allows us to pinpoint the locations of powerful particle accelerators, like pulsar wind nebulae, and to test theories about the nature of dark matter itself. How does the peculiar distribution of this antimatter challenge our view of cosmic evolution? It suggests that the universe's most violent explosions are not just destructive, they are also prolific seeding events. A single supernova or a merging pair of neutron stars can flood local space with these exotic particles, creating temporary antimatter currents that flow through the galactic web before their inevitable, luminous end. This reverse flow reveals a universe where creation and destruction are two sides of the same coin, and where the most fleeting pathways can illuminate the deepest truths. A supernova remnant is the ultimate cosmic factory, forging the raw materials for the universe's invisible highways. The violent shock wave from an exploded star, like the brilliant Cassiopeia A, expands for thousands of years, plowing through the surrounding gas at millions of kilometers per hour. This shock front is not a simple wall. It is a turbulent, magnetized boundary that acts as a natural particle accelerator of almost unimaginable power. Charged particles, mostly protons and electrons, become trapped in this chaotic region. They bounce back and forth across the shock wave, gaining a little more speed with each crossing, like a surfer being pushed repeatedly by a perfect wave. This process, known as diffusive shock acceleration, can hurl these particles to nearly the speed of light, injecting them as high-energy cosmic rays directly into the galactic magnetic field system. These stellar cataclysms are the primary on-ramps for the cosmic ray traffic flooding our galaxy. We know this because our telescopes see the unmistakable signatures of this furious activity. In X-ray light, we observe the brilliant glow of synchrotron radiation, a telltale sign of electrons spiraling at relativistic speeds along magnetic field lines within the remnant. Even more telling are the gamma rays we detect, which often reveal the specific fingerprint of pion decay. This occurs when a proton, accelerated to a tremendous energy, smashes into a slower-moving proton, creating a short-lived particle that almost instantly decays into gamma rays. This is the direct evidence that these remnants are not just accelerating lightweight electrons, but the atomic nuclei that make up the bulk of cosmic rays. But these factories do more than just create fast-moving particles. They also shape the very roads they will travel on. The expanding shock wave generates immense turbulence, twisting and amplifying magnetic fields throughout the surrounding space. This creates a scattered landscape that both guides and scatters the newly launched cosmic rays, setting them on their long, winding journeys. Simultaneously, the supernova enriches the interstellar medium, seeding it with heavy elements forged in the star's core and during the explosion itself, from the oxygen we breathe to the iron in our blood. This enriched gas becomes the raw material for future stars and planets, and the very obstacle course that future cosmic rays will navigate. The role of a supernova remnant evolves over its long lifetime. A young, fast-expanding shock is an efficient accelerator, while an older, slower remnant eventually loses its ability to confine particles, allowing them to leak out into the wider galactic magnetic highway. What role do these stellar explosions play in maintaining the cosmic ray flux? They are the steady, rhythmic heartbeat of the galaxy's particle circulation, ensuring a constant supply of energetic travelers. Their impact reverberates for millennia, shaping the chemical and energetic landscape of the entire Milky Way. Yet, for all their immense power, supernovae are not the most extreme particle accelerators in the cosmos. The galaxy M87 harbors a true cosmic monster, a supermassive black hole whose gravitational pull is so immense it warps spacetime itself. Yet from this point of ultimate destruction erupts one of the most spectacular displays of creation in the universe, a jet of plasma stretching for 5,000 light-years, a linear highway of pure energy. This is an active galactic nucleus, NAGN, and it represents particle acceleration on a scale that defies human comprehension. At the heart of this system, the black hole's intense gravity draws in vast quantities of gas and dust, forming a superheated accretion disk that shines brighter than all the stars in its galaxy combined. But not all that material falls in. Through processes that astrophysicists like Roger Blandford have theorized, the black hole's immense rotational energy and powerful magnetic fields can act like a cosmic slingshot, flinging a fraction of the infalling matter away in two opposing, tightly focused jets. These jets move at velocities so close to the speed of light that they are described as relativistic, carving pathways through intergalactic space for millions of years. The particles within these beams, electrons and protons accelerated to unbelievable energies, become the most extreme long-distance travelers in the cosmos. They do not travel silently. As these charged particles spiral along the jet's magnetic backbone, they emit a brilliant symphony of radiation across the entire electromagnetic spectrum. From the long, steady waves of radio light that first revealed these structures to our telescopes, to the blistering, high-energy gamma rays that signal the most violent processes, every photon tells a part of the story. We now know these jets are also sources of the universe's most elusive particles, firing off high-energy neutrinos and cosmic rays that eventually find their way across the cosmic web. The impact of these particle cannons extends far beyond their brilliant light show. When an AGN jet plows into the tenuous gas that exists between galaxies, the intergalactic medium, it acts like a colossal blender. The jet transfers immense energy, heating the gas, preventing it from cooling and collapsing to form new stars. This process, known as feedback, is a crucial thermostat for galaxy growth. Without these periodic blasts from central black holes, galaxies might grow too large, too fast, forming far more stars than we actually observe. The AGN effectively regulates its own galaxy's development and the development of its neighbors by flooding the local cosmic environment with a storm of energetic particles. How do these distant, explosive events shape the pathways available to particles across the entire universe? Their jets create permanent magnetic corridors, channels that guide the flow of energy for eons. They are the master architects of the invisible highways, demonstrating that the largest structures in the cosmos are intimately connected to the smallest particles. This vast bubble of solar influence, the Heliosphere, is our local neighborhood's particle highway. It stretches far beyond the orbit of Pluto, a protective shield defined by the relentless outward flow of the solar wind. Within this immense structure, the Sun's magnetic field and particle streams carve out a complex network of pathways, a miniature cosmic web right in our own celestial backyard. The boundary of this entire system is the heliopause, a distant frontier where the pressure from the solar wind finally balances against the gentle push of particles and magnetic fields from the space between stars. It is here that the Sun's domain truly ends. When the Voyager 1 probe crossed this invisible barrier, it sent back data that stunned scientists. Instead of a simple, smooth transition, the spacecraft encountered a turbulent, frothing region, a magnetic barrier that acts like a cosmic filter. This discovery revealed that our protective bubble is not a perfect shield, but a dynamic and complex interface, constantly interacting with the galaxy beyond. This local system has a direct and tangible impact on our technological world. The heliosphere modulates the flood of galactic cosmic rays, those high-energy particles from distant supernova. During periods of high solar activity, the heliosphere swells and becomes more turbulent, deflecting more of these external rays. When the Sun is quiet, the bubble contracts and weakens, allowing more cosmic radiation to seep into the inner solar system. This directly affects space weather, influencing satellite operations, astronaut safety, and even the chemistry of our own upper atmosphere. The constant dance between the solar wind and interstellar particles at the heliopause creates a region of intense study. What is the precise nature of this interaction? How are particles from outside our solar system processed and filtered as they enter? By understanding this local particle highway, we gain a powerful model for interpreting far larger structures. The processes at work at the heliopause, the shaping of a bubble by a central source of energy and wind, are echoes of what happens around other stars and even entire galaxies. Mapping the flow of particles through our own celestial neighborhood provides the key to reading the stories carried by travelers from the deepest reaches of the cosmos. A gamma ray burst unleashes more energy in a few seconds than our Sun will release across its entire 10 billion-year lifetime. This is not a broad, expanding fireball, but a focused event. A pair of narrow jets erupting in opposite directions at over 99.9% the speed of light. These jets are the universe's ultimate particle freeways, unimaginably intense and tragically brief. For the span of a heartbeat, They create a channel of pure energy, a temporary corridor through which particles are accelerated to limits that challenge our understanding of physics. Missions like NASA, a swift satellite, have been our sentinels for these fleeting cataclysms. As the late astrophysicist Neil Gehrels, the mission's namesake, once noted, Swift turned these mysterious flashes from theoretical curiosities into observable, detailed phenomena. The satellite's rapid slewing ability allows it to catch the brilliant initial flash of gamma rays, and then pivot instantly to study the lingering afterglow that shines for days in X-ray, optical, and radio light. It is in this fading echo that the true story unfolds. The afterglow is not the explosion itself, but its aftermath, a continuing emission generated as the jet plows into the surrounding gas, a shock wave that acts as a long-lived particle accelerator. The photons that travel to us from these events are more than just messengers of a distant explosion. They are cosmic probes. As they traverse billions of light-years of intergalactic and interstellar space, their journey is subtly altered. Hydrogen gas in distant galaxies absorbs specific wavelengths, imprinting a barcode-like pattern on the burst spectrum that lets us sense the composition of matter across cosmic time. The particles themselves, electrons and protons caught in the jet's fury, are boosted to energies that may explain the origin of the very highest energy cosmic rays we detect showering our own atmosphere. What is the engine capable of such a focused, violent release? The evidence points to two primary origins, each leaving a distinct fingerprint. Long-duration bursts, lasting more than 2 seconds, are thought to be the birth cries of black holes, created during the collapse of a massive, rapidly spinning star. Shorter bursts, mere milliseconds long, are the death rattles of binary neutron star systems, as these incredibly dense objects spiral together and merge, likely forming a black hole in a final, glorious burst of gravitational and particle energy. This transient nature makes them a stark contrast to the steady, rhythmic pulse of a supernova remnant or an active galactic nucleus. They are the cosmic equivalent of a lightning strike, an instantaneous, brilliant flash that illuminates the landscape for a single moment before vanishing. How do these brief freeways influence the long-term particle background of the cosmos? Their incredible power suggests that, while each is fleeting, the collective contribution of countless bursts across the universe's history may have fundamentally shaped the energy density of intergalactic space, leaving a diffuse, high-energy particle background that is the summed whisper of a trillion ancient flashes. Beyond the brilliant beacons of supernova and the focused jets of black holes lies a far more subtle light. This is the universe's background hum, a diffuse glow that permeates all of space. The most famous of these is the cosmic microwave background, the ancient afterglow of the Big Bang itself, a fossilized snapshot of the universe in its infancy. But there are other, more modern backgrounds as well. The entire sky shimmers with a faint, persistent gamma-ray glow, a light our eyes cannot see, but one that our most sensitive telescopes can map. This is not the light of any single star or galaxy. It is the cumulative signature of a trillion invisible journeys, the combined light from countless particle interactions happening across the vastness of space. Every time a cosmic ray proton smashes into a stray hydrogen atom in a dark cloud, it produces a flash of gamma radiation. Each of these flashes is incredibly faint on its own, but when you add them all up, across the entire galaxy and beyond, they create a pervasive, detectable luminosity. It is the light of the cosmic ray highways themselves, a map of their traffic written in the most energetic language the universe possesses. Space telescopes like NASA Fermi have spent years carefully charting this gamma-ray background, peeling it apart from the brighter, more localized sources. What they reveal is the silhouette of our own Milky Way, not in starlight, but in the glow of destruction, a testament to the endless rain of high-energy particles upon the galactic gas. But the story does not end there. This background also contains a more mysterious component, an isotropic glow that comes from all directions equally from beyond our galaxy. This is the integrated light of every unresolved active galactic nucleus, every distant gamma-ray burst, and every other high-energy event throughout cosmic history, their individual voices blended into a single, steady choir. How do scientists use this faint, all-sky hum? It serves as a powerful constraint, a reality check for our models of the cosmos. By calculating how many gamma rays should be produced by all the known cosmic ray interactions and astrophysical sources, and comparing that to the background we actually observe, we can test our understanding. If the models predict too much light, we are missing something about how particles lose energy. If they predict too little, we might be overlooking an entire population of faint sources, or even a signature of something more exotic, like the annihilation of dark matter. This diffuse glow encodes the total energy budget of the universe's particle traffic. It tells us about the history of star formation, because more stars lead to more supernova, which means more cosmic rays and more gamma rays. It reveals the efficiency of cosmic magnetic fields at confining these particles. It is the ultimate integrated record, a census of the invisible activity that has shaped our cosmos from the beginning. This pervasive background is the context for every individual particle detection, the steady static against which we search for the unexpected signal, the subtle anomaly that could rewrite our entire story. The cosmic ray spectrum should be a smooth, sloping line, a predictable decline from low to unimaginably high energies, but it is not. Instead, our most precise detectors reveal sharp bends and unexpected bumps, like mysterious detours on a road map we thought we knew. These features have names that speak to their puzzling nature: the knee and the ankle. At the knee, around 1 million trillion electron volts, the spectrum steepens dramatically. It is as if a cosmic toll booth has appeared, suddenly removing a huge portion of the travelers. Then, at the much higher energy of the ankle, the spectrum flattens out again, suggesting a new population of particles, perhaps from beyond our galaxy, has joined the flow. Even stranger is the positron excess, a rising bump in the antimatter signal that our standard models of supernova remnants simply cannot produce. These are not minor errors in our charts. They are fundamental challenges to our understanding of the invisible highways. What could possibly cause such a sharp bend in the road? The knee may mark the energy limit for our galaxy's own magnetic confinement. Perhaps particles beyond this energy are simply too powerful to be held by the Milky Way's magnetic fields, escaping into intergalactic space and depleting the local traffic. Or maybe it signifies the maximum power of our most common galactic accelerators, the supernova remnants themselves. The positron surplus presents a different kind of puzzle. When the alpha magnetic spectrometer confirmed this anomaly, it forced physicists to consider radical new sources. Could these extra positrons be coming from a local cosmic engine, like a nearby pulsar whose furious wind is flooding our neighborhood with antimatter? Or does this bump contain the first, faint signal of dark matter, with the mutual annihilation of these invisible particles producing the electron and positron pairs we detect? Researchers like Stefan Funk have used powerful instruments such as the HESS observatory to peer at potential sources, comparing the gamma-ray light from pulsars to the predicted positron flux. The data is teasing, pointing to pulsars as a likely contributor, yet not entirely ruling out more exotic possibilities. To explain these detours, scientists are being pushed to redraw their maps entirely. They are revising the complex transport models that describe how particles diffuse and lose energy on their million-year journeys. They are proposing entirely new classes of cosmic accelerators, perhaps hidden within our galaxy or roaring from distant active nuclei. Every unexplained bump in the data is a signpost pointing toward a piece of missing physics, a source we have not yet imagined, or an interaction we do not yet understand. The secrets held within these spectral irregularities are profound. They could reveal the ultimate power limit of nature's particle accelerators, or they might finally illuminate the true identity of the dark matter that shapes our universe. Resolving them is not just about fixing a chart. It is about discovering entirely new continents on our cosmic map. An ultra-high-energy cosmic ray pierces the void between galaxies, a solitary traveler on an intergalactic freeway. This particle, likely a proton carrying the energy of a professionally thrown baseball, did not begin its journey in our Milky Way. Its origin lies in the heart of a distant active galactic nucleus, a monstrous black hole whose jet launched it across the cosmos millions of years ago. Its path is not a straight line, but a gentle, immense curve dictated by the faintest of extragalactic magnetic fields, weak but stretching across unimaginable distances. These are the ultimate long-haul routes, highways that connect entire galaxy clusters. The journey is a constant battle against the expanding universe itself. As space stretches, the particle's immense energy is slowly sapped, its wavelength stretched in a process known as the inverse Compton effect, where it loses energy to the faint glow of ancient starlight. It also navigates a sparse but present intergalactic medium, a thin soup of ionized gas and dark matter that can subtly scatter and deflect it over eons. How do we possibly trace such a ghostly traveler back to its home? The Pierre Auger Observatory in Argentina uses an entire landscape as its detector. Instead of a traditional telescope, it employs a network of 1,600 water tanks spread over 3,000 square kilometers, waiting for the massive air shower created when one of these ultra-high-energy particles finally strikes our atmosphere. By analyzing the arrival direction of billions of secondary particles, scientists can point back toward the source. The challenge is immense. Even the weak magnetic fields between galaxies bend the path of these charged particles, blurring their point of origin across the sky. It is like trying to trace the path of a single leaf caught in a hurricane. Yet, Auger has achieved a remarkable feat, correlating the arrival of the most energetic cosmic rays with the locations of nearby active galactic nuclei. This confirms that the particle traffic we see is not just a local phenomenon, but a grand intergalactic exchange. These extragalactic highways carry a unique cargo of information. They bring us direct samples of matter from other galaxies and news of cataclysms that occurred when the universe was young. They contribute the very highest energy particles to our local cosmic ray population, the ones that supernova in our own galaxy simply cannot produce. This broader view forces us to see the cosmos not as a collection of isolated islands, but as a single, connected ecosystem. The flow of particles along these immense corridors demonstrates that no galaxy is truly an island. Each one is constantly being seeded and influenced by events in the farthest reaches of space. What does it mean for our own Milky Way to be constantly bathed in this rain of visitors from distant shores? The next generation of cosmic cartography is already taking shape on remote mountaintops and in pristine Antarctic ice. Soon, observatories like the Cherenkov Telescope Array will not merely detect gamma rays. They will map them with a precision once thought impossible. This vast network of over 100 telescopes spread across 2 continents will act like a galactic traffic control system, watching for the faint, blue flashes of Cherenkov light created when high-energy gamma rays hit our atmosphere. It will provide a high-definition view of the particle accelerators scattered across the sky, revealing the structure of their magnetic highways in stunning detail. As one project scientist put it, we are moving from seeing the headlights of individual cars to mapping the entire flow of traffic on the cosmic freeway. This leap in resolution will allow us to watch how shock waves in supernova remnants funnel and accelerate particles, testing our theories of diffusive shock acceleration in real time. Alongside these powerful eyes on the ground, new space-based neutrino detectors are being designed to catch more of those elusive ghost particles. These instruments will turn the entire Earth into a telescope, using our planet as a shield to filter out background noise while they search for the unique signatures of neutrinos from specific cosmic cataclysms. The true power, however, lies in combining these tools. We are entering the golden age of multi-messenger astronomy, an era where a single event like a neutron-star merger can be observed through its gravitational waves, its flash of gamma rays, its burst of neutrinos, and the subsequent rain of cosmic rays. Each messenger particle travels a different highway, and by triangulating their arrival, we can pinpoint their origin with an accuracy that was once a fantasy. A gravitational wave tells us of the massive objects that collided. A neutrino reports directly from the heart of the engine, and a cosmic ray carries the material fingerprint of the source itself. Together, they provide a complete dossier on a cosmic event. This synergistic approach is powered by radical advances in computing and sensor technology. New detectors can scan the entire sky in real time, automatically alerting other observatories worldwide the instant a significant transient event occurs. This global network can then swing into action, capturing the fleeting light of a gamma ray burst or the rising tide of particles from a solar storm from every conceivable angle and wavelength. Supercomputers will run increasingly sophisticated simulations, digesting this torrent of multi-messenger data to create dynamic, living maps of our galaxy's magnetic fields and particle densities. How will these innovations transform our understanding? They will allow us to finally resolve the century-old mystery of the sources of ultra-high-energy cosmic rays, tracing those incredibly rare particles back to their extragalactic layers. They will provide the sensitive, all-sky monitoring needed to catch the faint, predictable whisper of dark matter annihilation or decay. The coming decade of discovery promises to reveal the full, dynamic complexity of the cosmic web, not as a static map, but as a living, breathing system of invisible highways, its traffic flowing in rhythms we are only beginning to perceive. A silent, persistent rain from space has been falling upon our world since its very beginning. This is not water, but a drizzle of high-energy particles, cosmic rays that have subtly shaped the story of life itself. While our atmosphere shields us from their most direct effects, a fraction of these travelers always reaches the surface, carrying just enough energy to leave a mark. Each particle can act like a microscopic bullet, capable of piercing a cell and snipping the delicate ladder of our DNA. Most of the time, the cell repairs this damage. But sometimes the repair is imperfect, and a mutation is born. Over the immense stretches of geological time, this constant, low-level bombardment has provided a steady trickle of genetic variation, the raw material for evolution. It is a humbling thought that the same violent events which destroy stars may have, in a roundabout way, helped to drive the diversity of life on our planet. The influence of these particles extends beyond the double helix. They tear through our atmosphere, colliding with molecules and creating showers of secondary particles. These cascades can break apart stable molecules and forge new, more reactive ones, influencing the very chemistry of the air we breathe. In the planet's deep past, this process may have played a role in the formation of complex organic molecules, the precursors to life. Astrobiologists like Paul Davies have long pondered this dual nature. Cosmic rays are a destructive force, a threat to biological molecules and a hazard for long-term space travel. Yet, they are also a potential catalyst, a source of energy that could have driven the chemical reactions that led to the first living systems. This creates a fascinating cosmic balance. Too dense a flux of particles, and life is sterilized. Too sparse, and the gentle nudge of mutation and chemical innovation might be lost. Our planet's experience of this particle rain is not constant. It ebbs and flows with the rhythm of our Sun. During periods of high solar activity, the heliosphere swells, deflecting more galactic cosmic rays and reducing the radiation reaching Earth. When the Sun is quiet, the shield weakens and the background radiation on our planet increases. Even our location in the galaxy matters. A solar system orbiting in a dense region of star formation would be subjected to a far more intense particle storm, potentially creating a much more challenging environment for life to arise and persist. This reveals a profound connection. The grand, invisible highways that channel particles across the galaxy do not end in the void. They terminate on worlds like our own, delivering both peril and possibility. The very mutations that lead to disease can, over generations, also be the source of adaptation and resilience. How deeply is the history of life on Earth intertwined with the particle traffic of the Milky Way? These biological impacts force us to look forward, to consider the ultimate fate of all this cosmic matter streaming through the void. Every journey on these cosmic highways must eventually reach its end. A proton that once surfed magnetic fields at near light speed finally drifts into a cold, dark molecular cloud. Here, it slowly sheds its immense energy, not in a violent collision, but through countless tiny interactions, ionizing atoms and gently heating the gas until it is just another constituent of the interstellar medium. This is not a death, but a transformation. That same proton, now stripped of its cosmic ray identity, becomes part of the raw material for a future star, a planet, or perhaps even the building blocks of life. The destinies of particles are as varied as their origins. Some are absorbed directly by worlds or stars, their journey terminated. Others, like free neutrons, have a limited lifespan and will spontaneously decay into a proton, an electron, and an antineutrino after about 15 minutes. But the most profound fates involve feedback, a process where the particles actively shape the environment they travel through. As cosmologist Martin Rees once noted, the energy deposited by cosmic rays and other high-energy particles provides a crucial heating mechanism in galactic gas clouds. This gentle warming can prevent the gas from cooling and collapsing under its own gravity, effectively putting a brake on the formation of new stars. It is a self-regulating cycle, where the violent death of one generation of stars, which produces the cosmic rays, directly influences the birth rate of the next. This cosmic ecology extends into the hearts of stars themselves. In the Sun's core, the neutrinos we discussed earlier carry away a fraction of the fusion energy as they stream outward. This energy loss subtly cools the stellar interior, influencing the star's lifetime and the intricate processes that lead to its final supernova. In the final moments of a massive star's life, a torrent of neutrinos carries away over 99% of the gravitational binding energy, and this neutrino pressure is the very mechanism that drives the supernova explosion, recycling the star's enriched contents back into the galaxy. This continuous flow is the universe's great recycling program. The iron in your blood, the oxygen in your lungs, and the calcium in your bones were all forged in stellar furnaces, and then scattered across space by the very particle winds and explosions that define these cosmic pathways. The endpoints of these journeys are not final stops, but transfer points in an endless cycle. How does this grand circulation shape the universe over billions of years? It dictates the pace of star formation, the chemical enrichment of galaxies, and the very conditions necessary for planets and life to emerge. Understanding where the particles end their travels completes the story, revealing a cosmos not just in motion, but in a state of perpetual, dynamic rebirth. Beyond the familiar dimensions of space and time lies a landscape of pure geometry. String theory, our most ambitious map of reality, suggests the universe is woven from vibrating strands of energy. These strings do not dance only in the 3 dimensions we know. They resonate through a cosmos of 10 or more dimensions, most of them curled into sizes so infinitesimally small they escape all notice. Within this hidden architecture, the highways for particles could be far stranger than magnetic fields or gravitational curves. They might be shortcuts through the higher dimensional bulk, routes that would appear as magic from our limited perspective. A particle might vanish from one point in our space and reappear at another, not because it traveled faster than light, but because it took a more direct path through a dimension we cannot see. Physicists like Lisa Randall have pioneered models where our entire universe is a three-dimensional membrane, or brain, floating within a higher dimensional reality. In such a world, the force of gravity, uniquely weak in our experience, could be spilling into these extra dimensions, its strength diluted across the full fabric of the cosmos. What if dark matter is simply matter sequestered on a parallel brane? Its gravitational whisper the only evidence of its existence. The implications for particle travel are profound. A cosmic ray that seems to arrive with impossible energy might not have been accelerated by a shock wave. It could have slipped through a fold in the dimensional fabric, a topological shortcut that bypassed the normal routes entirely. Testing such a radical idea demands incredible precision. Scientists search for tiny deviations in how particles interact, or subtle anomalies in the cosmic ray spectrum that our standard three-dimensional models cannot explain. They look for particles that appear to lose energy in ways that suggest a leak into other dimensions. The Large Hadron Collider hunts for evidence of these extra dimensions by searching for missing energy and momentum in its collisions, a telltale sign that something has escaped our dimensional plane. While these shortcuts remain speculative, they force us to reconsider the very nature of a pathway. The invisible highways we have mapped across the galaxy may be mere surface streets on a far grander, multidimensional freeway system. This speculative view inevitably draws us down to the smallest scales, where the nature of the roads themselves becomes a question of quantum uncertainty. An electron's journey is not a single, definite line. It is a spray of possibilities, a wave of probability fanning out across the void. This quantum nature, so often confined to the tiny realm of atoms, stretches its influence across light years. The path of any particle is not a railroad track but a blurry corridor of where it could be, its exact location and momentum forever coupled in an uncertain dance. This is not a small-scale quirk. It is the fundamental reality underlying every cosmic highway we have mapped. In the crushing density of a neutron star's crust, this quantum uncertainty becomes a powerful engine. Here, particles like protons can face what seems like an impenetrable energy barrier. Yet, thanks to their wave-like character, there is a finite, calculable chance they will simply appear on the other side, a process we call quantum tunneling. This isn't magic, it's mathematics, and it provides a crucial mechanism for particle escape and acceleration in some of the most extreme environments in the universe. The physicist Richard Feynman captured this beautifully with his sum over history's approach, suggesting a particle explores every possible path between 2 points, with the most probable one being the one we ultimately observe. For the most energetic particles ever detected, those cosmic rays carrying the energy of a pitched baseball, the fabric of spacetime itself may begin to fray. At these extreme energies, the tiny, frothing grain of space predicted by theories of quantum gravity might become significant. The very road these particles travel on could be bumpy at a scale we cannot yet see, potentially altering their speed or creating subtle detours over billions of light years. This probabilistic layer transforms our map of the cosmos from a fixed network of roads into a living, breathing probability cloud. We can no longer say a particle will take a specific route, only that it is most likely to flow through certain channels. How do we reconcile this fuzzy, quantum underpinning with the seemingly predictable paths we chart? For most cosmic journeys, the classical approximation works brilliantly. Much like we don't need quantum physics to design a highway. But to understand the deepest origins and the most extreme travelers, we must eventually descend to this foundational level, where the roads themselves are born from probability. We stand at the confluence of invisible rivers, observers of a cosmic flow that has shaped our very atoms. This knowledge irrevocably alters our perspective, shrinking our world to a fragile speck while simultaneously connecting us to the grandest processes imaginable. The vast majority of the universe's activity is hidden from our direct senses, a silent, energetic dance we can only perceive through the language of mathematics and the ingenuity of our instruments. This challenges our most basic assumptions about reality, forcing us to accept that what we see is only a tiny fraction of what actually is. The late astronomer Carl Sagan captured this profound shift when he reflected on our pale blue dot, a world made from star stuff, adrift in a cosmic ocean. We are not just living on a planet, we are embedded within an immense, dynamic system of energy and matter, its pathways etched into the fabric of space itself. This cosmic context carries its own ethical weight. The immense resources required to build observatories and fund deep space missions are often questioned. Why look to the heavens when there are pressing problems here on Earth? The answer lies in the unforeseen returns of pure curiosity. The technology developed to track cosmic particles has led to advances in medicine, computing, and materials science. More fundamentally, this pursuit answers a deep human need to understand our origins and our place in the scheme of things, a quest that has driven progress for millennia. This exploration also forces us to consider a future where we might not be the only ones watching the particle flow. If we were to detect a pattern in the cosmic rays, an artificial signal etched into the high-energy spectrum, it would represent the most profound discovery in human history. How would such knowledge change us? It would instantly transform humanity from a collection of competing nations into a single species, united by a shared cosmic heritage and a common future. This is why international collaboration is not just beneficial, but essential. No single nation can map the cosmos alone. Projects like the planned IceCube Gen 2 telescope or the Cherenkov telescope array are testaments to our collective desire to understand, bringing together scientists from across the globe to read the story of the universe. Understanding these particle pathways does more than satisfy scientific curiosity. It provides a humbling and unifying vision of our existence. We are temporary custodians of stardust, granted a brief moment to look up and trace the invisible roads that brought us here. This cosmic perspective is not a luxury. It is a vital part of navigating our future on this planet and beyond. Our journey along the invisible highways reveals a cosmos deeply interconnected by the flow of particles. We have traced the paths of cosmic rays surfing magnetic fields, ghostly neutrinos traveling in perfect lines, and photons whose very routes are bent by the gravity of unseen matter. These are not separate stories, but different lanes on the same cosmic freeway. A dynamic network where acceleration, interaction, and propagation link the very small to the impossibly large. The energy from a dying star can influence the birth of another, and the subtle rain of particles upon our world may have nudged the course of life itself. Every detection, every flash of light in a distant ice sheet or a tank of water on a high plateau, carries a story of a cataclysmic event from the deep past. Mapping these highways does more than satisfy our curiosity. It enhances our understanding of star formation,